This slide shows an example of decision tree on retail data. Here we are trying to find if a customer will redeem a coupon or not. So if the customer is a loyal customer, if that's yes, and if the household income is less than 150K, then yes, the customer will redeem a coupon. If the household income is greater than 150K, and there is another node here where it is checking if the shopping mode is online or store. If it's store, then yes, the customer will redeem the coupon. If it's online, then no, the customer will not redeem the coupon. If the customer is not a loyal customer, then we look into last month's spend. If the spend is less than $100, then no, the customer will not redeem the coupon. But if the last month's spend is greater than or equal to $100, then yes. If the coupon placement is A, then no, the customer won't redeem the coupon. If it's B, then yes, the customer will redeem the coupon. So this slide it shows the rule set model. Here, if the customer is loyal and the household income is greater than or equal to 150K, and the shopping mode is store, then yes, the customer will redeem the coupon. So that's what this statement says. If loyal customer is equal to yes, and then the household income is greater than or equal to 150K, and the shopping mode is equal to store, then coupon redemption is equal to yes. So in this slide, we look into various terminologies in the decision tree. So a decision tree is made up of several nodes. So the top node, it's known as the root node. And then the nodes that are internal, they are known as the internal node. So the line that connects each node is known as branch. And then the node at the end, it's known as the leaf node. So this slide, it shows the best binary partitioning. First, we have the regression tree, and then the classification tree. The regression tree is used when we have continuous variables in the data. So here the output is real numbers. The classification tree is used when we have categorical data. And here the output is on categories. So here the category is whether yes or no. So here the prediction is done based on the average of existing data. So the average of these values is 3.36 and average of this is 9.7. So based on the average of the values, the prediction is done. And then here the SSE means the sum of squared errors. So it is the square of the error between the anticipated values and the actual values. So yeah, we want this to be minimum. And then here the Gini index, it shows it is used for measuring the error too. So we want the Gini index value it to be as low as possible. If it's small, then it means the decision tree is more ordered. So here the prediction is made based on the majority. Here the majority classification is no. So we have the final prediction as no. And then here the majority classification is yes. So the prediction is yes. So here the main objective is we need to minimize the dissimilarity in the terminal nodes. Let's move on to the next slide. In this slide, we see how we can minimize the loss function. So if it's a numeric feature, then the numeric value it's split in order to minimize the loss function. So here we can see a split is made between 1, 2, 3 and then 4. So if the x value is less than or equal to 3, then it goes to this class, and if the x value is greater than 3, then it goes here. For the binary feature, the category is split in order to minimize the loss function. So if it's short or tall, then if it's short, it goes to this node, and then if it's tall, then it reaches this node. For a multi-class feature, order feature classes based on mean target variable for regression trees or based on the class proportion for classification. And then we choose the split in order to minimize the loss function. So it can be seen here for the multi-class feature. So we split based on the feature, and then if this condition is satisfied, then it reaches this branch, else it reaches this branch. So in this slide, we see a decision tree where the depth of the tree is 1. So here it has 2 terminal nodes. The terminal nodes, they are also known as the leaf nodes. And then the graph here, it shows where the split is done when building this decision tree. In this slide, we look into the decision tree where the depth of the tree is 3. So initially we have the root node, and then its depth is 1, 2, and then 3. Finally we have the terminal nodes at the bottom, and this graph shows how the tree looks like when plotted. So in this slide we look into a more complex decision tree. Here the depth of the decision tree is 20. As you can see, there are several nodes involved in building this tree, and this graph over here, it shows the decision tree with the depth 20 plotted in a graph. So this slide is on 2 predictor decision boundaries. We have a classification problem. We have iris data. So here we need to classify the flower species as either setosa, versicolor, or virginica. So based on here, we see a graph where the y-axis shows the sepal width, and then the x-axis is the sepal length, and then this plot here, it shows a scatter plot of the species based on those values. In this slide, we look further into the iris data. So the graph here, it shows that the orange portion of the graph, it belongs to setosa species. The green portion belongs to virginica, and the gray portion belongs to the versicolor. So here the classification tree is shown. Initially we assume the class, the species to be one like a setosa, and then from there we ask questions. If the feature belongs to this value, then it gets classified as one type, else another type. So this shows how the decision tree is built based on the sepal length comparison, sepal width, and then further like with different values of sepal length and sepal width. So finally we arrive at the conclusion whether the species belongs to setosa, versicolor, or virginica. This slide, it shows how to address a major problem that occurs in decision trees, which is overfitting. Overfitting is where the model, the decision tree model becomes too perfect and that it predicts almost accurately in the training data, but when using the test data, the accuracy is not much at all. So that's the problem with overfitting. So it's necessary that we minimize this overfitting. So one way to do that is we need to stop early. So first way to do that is, in order to limit the tree depth, we need to stop splitting after a certain depth. Another way to do this is to minimize the node size. So if the intermediate node contains very few data points, then it's best that we do not split it further. So these graphs are related to that. Another way to minimize this overfitting is by using pruning. What pruning does is it reduces the size of the decision trees by removing sections of the tree that are uncritical or redundant. So we grow a very large tree and then prune it back with a cost complexity parameter alpha multiplied with the number of terminal nodes t in order to find an optimal subtree. So this approach is very similar to the lasso penalty that is used in regularized regression. So lasso, it stands for least absolute shrinkage and selection operator. So for a large alpha, it means it is a small tree, and small alpha means a large tree. We need to find an optimal alpha with the cross validation. So we minimize it by using the loss function plus the alpha in product with the number of terminal nodes. So that's what here this graph shows, that the deep trees, they overfit, and we need to penalize their depth in order to generalize. This slide shows the strengths and weaknesses of decision tree. So these are the strengths. Small trees, they are easy to interpret. The tree, it scales well to large n fast, and it can handle data of all types, and it requires very little if no pre-processing. And then here we can do automatic variable selection, and it can handle the missing data, and it's completely non-parametric. So these are some of the weaknesses of the decision trees. The large trees, they are very difficult to interpret, and all the splits, it depends on previous splits, that is capturing the interactions and additive models. The trees are step functions, that is there are binary splits in it, and then the single trees, they have a very poor predictive accuracy rate, and then single trees, they have very high variance too. It's very easy for them to overfit the training data, so that the final test data prediction becomes poor. So as we see here in these graphs, it shows that how the single pruned trees are poor predictors. So that's one of the main weaknesses of decision trees, and how the single deep trees, they are noisy. So these trees that are deep, they are very noisy and impure. So these two disadvantages are made into an advantage by using a concept called bagging. So this bagging, it uses this high variance to our advantage. So what is bagging? Bootstrap aggregating is known as bagging. So here the sample records with replacement is known as bootstrap. We bootstrap the training data. This is the original training data, and then we bootstrap this data into several samples. So what is sampling? Sampling, it is the process of selecting a subset of items from a vast collection of items. So from this vast collection of items, we just take a subset and then prepare a sample. So what is bootstrap? Here sampling with replacement is known as bootstrap. So it means a data point in a drawn sample, it can appear in future drawn samples as well. So again and again they get repeated. So these are some of the bootstrap samples that's created from this original tree. Second step is we fit an overgrown tree in order to each of the resampled data set. So each of the overgrown tree is fit into the resampled data set. And finally, the prediction is based on the average of these. So the average of these trees are then used for making the final prediction. So this slide, it shows the advantage of using bagging. As we add more trees, our average prediction error, it reduces. So this graph shows how as more trees get added, the prediction loss, it reduces. So instead of having a single building trees with the original data, we create several bootstrap samples and then take an average of the trees created with that, so that our average prediction error, it gets reduced. So in this slide, we look into the random forest algorithm. So this shows the simplified version of the random forest. So random forest, it is identified as a collection of decision trees. So it's not a single decision tree, it's a collection. That's why we have the name random forest. Each tree, it estimates a classification, and this classification is called a vote. Ideally, we consider each vote from every tree and then choose the most voted classification, that is majority voting. So let us consider an example where we have an instance, a record from our data set. We are passing it to the random forest. So what happens is simultaneously it is passed into several trees. So in each tree it takes a path and arrives at a class decision. So this orange portion shows the path that this instance takes. So with the decision tree 1, it reaches the classification as A, and then for the tree 2 it reaches the class B by taking this path, and then for similarly it goes on for several trees, and then for the tree N it takes this path and then it gets classified as class B. So based on the average majority voting, so here from these three trees we can see the tree 1 it has class A, tree 2 has class B, and tree N it has class B. So based on majority voting the final class is decided. So here we can say the final class might be class B. So the random forest, they follow the same bagging process as the decision trees, but each time a split is to be performed, the search for the split variable, it is limited to a random subset of M of the P attributes, that is the variables or features. So here the split is based on the random subset M of the P. So this is known as split attribute randomization. For classification trees, the value of M is calculated as root of P, and for the regression trees it's calculated as P by 3, and M is commonly referred to as M trie. The main advantage is that random forests produce many unique trees, as we can see in this diagram. This slide shows the difference between bagging and random forest. So bagging, it introduces randomness into rows of the data, whereas random forest, it introduces the randomness into rows as well as the columns of the data. So when combined, this provides a more diverse set of trees that almost always lowers our prediction error. So this graph here, it shows the split attribute randomization, and we can see the prediction error is reduced here. This slide, it shows the random forest out of bag observations. For a large enough data set N, on an average 63.21% or the original record of the original records, they end up in any of the bootstrap sample, and roughly the remaining 36.79% of the observations, they are not used in but in the construction of a particular tree. So these observations, they are considered as out of bag observations, and they can be used for efficient assessment of the model performance. So some of the tips here are: when the value of n is small, the out of bag observations is less reliable than validation. But as the n value increases, OOB is far more efficient than the k-fold cross validation method. When the number of trees are about 3 times the number needed for random forest to stabilize, then the OOB error estimate is equivalent to the leave one out cross validation error. So this graph here shows the out of bag observations and then the test. So even though the random forest, it provides a very good out of the bag performance, there are a few parameters that we can tune in order to increase the performance of random tree some more. So one of that is the number of trees. Typically they have a largest impact on the predictive accuracy, and next is the M-trie. So they both are they both have very high impact on the predictive accuracy. Next is the node size and the sampling scheme. So they have marginal impact on the predictive accuracy, but it's still worth exploring that. We can also increase the computational efficiency by using making modifications to the node size and the sampling scheme. Finally, it's the split rule. It is used for increasing the computational efficiency. This slide shows some of the strengths and weaknesses of the random forest. The random forest, they provide competitive performance. They are remarkably good for the out of the box. That is, they have very little tuning that's required. They have a built-in validation set. We need not sacrifice the data for extra validation, and they typically do not overfit like the decision trees do, and it's robust to outliers, and it handles the missing data. We need not impute the data. It handles it by itself. And then it also provides the automatic feature selection, and there is very minimal pre-processing that's required when using the random forest. So it has so many strengths. So these are some of the weaknesses of the random forest. So even though they are accurate, it cannot compete with the accuracy of advanced boosting algorithms, and it can be slow. It can become slow on large data sets, and it's less interpretable. So this less interpretable problem, it can be addressed by using various tools such as variable importance, partial dependence, plots, line, etc.